Strange. Did the slide show up earlier? No? Okay. Let me try to do a few. Okay, somehow my slides are not projecting properly, so I'm going to power off the system and restart. Hopefully that will fix the problem. Sorry for the trouble. Okay, great. All right, looks like we're back on, we're recording. Okay, we're good. All right, sorry for the trouble. Let's get started. So we are starting, this is week 8. Okay, so today's Tuesday. So first, a couple reminders. We have our homework 4 out, okay? It's due this Thursday, okay? After that, we have one more, homework 5, which is the last homework. It will be posted by this Thursday, due next Thursday. So we'll be done with all the 5 homeworks by next Thursday, okay? After that, the week after, we're going to have the midterm exam, okay? So we have posted a survey in Canvas, so please go there, check. Basically, what we're doing, we're just checking like your plan for the midterm exam, okay? So most of you hopefully should be able to just attend in person during the class time. But like if you need any special accommodations, please make sure you fill out that form, and we will confirm how we set up things, because we have a few like different scenarios, so we want to make sure we have covered everybody. Okay, all right. So please finish that survey by this Thursday. Okay, so we can make sure we have everything set up ready for the actual exam. Okay, any questions regarding the midterm exam? Fine. Okay. All right. So in the previous lecture, we finished our discussion of chapter 6. Okay. So this is the starting discussion of classification. Okay. So at the high level, right, classification is widely used in data mining. Okay. Also in machine learning, there's a lot of research, right, of developing different classification methods, okay? So the basic understanding is that what do we mean by classification? What do we mean by supervised learning? What do we mean by training data versus the testing set? So those are all the, more like the problem setting, okay? So given the classification problem setting, there are different approaches, okay? So in chapter 6, we'll talk about a few kind of basic but widely used methods. Okay, so by now, hopefully you all know decision tree Bayesian classification. You know, like generally how they works and also the high-level properties. Okay, so one thing we say, decision tree is really easy to interpret because you basically have the tree, right, telling you how to make decisions along the way. Okay, while with the Bayesian classification, one thing that is also quite interesting and unique is about this statistical calculation, right? And because of that, you can actually do incremental classification, meaning that you don't need to reconstruct your model. Like decision tree, you basically have to redo everything when you have a new data set. While with Bayesian classification, you just need to update real probabilities, okay? All right, we also talk about lazy learning, linear classifiers, so those are some of the widely used methods, okay? We then dive into evaluation and also like how you can use ensemble to further improve the classification accuracy, okay? So there are quite a few things in terms of what kind of metrics do we care about, right? What do we mean by confusion matrix? What do we mean by false positive, false negatives, right? And there are different ways of calculating the different metrics depending on what you're interested in or what's more important for your particular application scenarios, okay? And then with ensemble, the main thing is about the weighting, right? Because ensemble says that, okay, instead of using one classifier, I want to use multiple classifiers. When you have multiple classifiers, then the things are how do you aggregate, right? Okay, simple way is that you do majority voting, so like whoever has, like whichever class label has the majority, right? Voting, then that's the one. But with the boosting, we say that, hey, they're not equal, right? We want to treat them differently. So you try to weigh them differently so that you can do the aggregated voting, but with like assigning different weights to different classifiers, okay? All right, now today we're going to continue, okay? We're still talking about classification, okay? But now we're going to cover some advanced methods. Okay, you say, okay, we have learned decision tree, we have learned the Bayesian classification, which are quite successful, right? So what else do we need to learn in terms of classification, okay? There are actually quite a few things, okay? So, so we're going to try to cover a lot of the high-level ideas, okay? We're not necessarily getting to all the like technical details to the point that you can implement all of this, but we want you to understand like why we need this approach, right? What are the key properties of those approach, okay? So when you look at the individual ones, you know like there are different choices, okay? And you may be able to use different methods for different scenarios, okay? So starting with the feature selection, right? We all know like with the classification, right? You need some way of say which features are most informative, right? So there are two related terms, okay? One is the feature selection, one is the feature engineering. You may have heard those terms under different scenarios, okay? The high level, right, as the name suggests, right? Feature selection basically says that, okay, I have all those features. Do I have a way of identifying which ones are more informative, okay? So like if you think about decision tree, right? With the decision tree, when you look at your training table, you have all those different attributes you could ask about, right? But which ones, okay? So decision tree has a way of identifying, right, which ones like you want to ask and how you do the splitting. But then there are also other approaches where you may be able to take existing features and then actually construct new features, okay? This is referred to as a feature engineering, okay? So before deep learning, okay, a lot of effort, right, in classification is actually spent on feature engineering, right? People spend a lot of time trying to look at the data, look at the domain, trying to understand which attributes are more informative, okay? Sometimes those are intuitive, right? If you're in a particular domain for your problem, you kind of know, right, which ones are likely to be relevant, right? If you think about your projects, right, many of your projects are trying to use different attributes to like provide certain predictions or modeling, like to like understand what is more likely to happen, right? So you probably have some idea about which attributes are more relevant, okay? So that's why a lot of that is like you can try to take existing attributes, right? Maybe construct new ones, okay? Then this is what say traditional, yeah, domain knowledge is the key, but deep learning has actually increasingly been shown to be able to like automatically identify the features, right, that are most informative, okay? Because it's, we'll cover deep learning later, but okay, by the high level, it is basically trying to pull in whatever data you have, right, and trying to look at a different granularity, there are different functions to combine those attributes, and then they have a way to train the neural network with different weights, right? That is in effect trying to figure out which attributes are more relevant, okay? So there are different ways to do this, okay? So you could do this as I say as a pre-step, meaning that like when you have your data set, right? So you start with what we call this is a filter methods, okay? So you have like original data set with all the attributes, right? You define some kind of measure, right? Okay, it's the goodness measure, okay? So that say, okay, like for example, like in a particular dimension, right? If you see like the mostly uniform information, the values are uniform. I mean, like if you take a population, everybody has the same major. Then you probably know, okay, this major is not going to be very like informative in terms of differentiating different classes, right? Okay. Rather, you may want to look for attributes that have a bit of kind of more like variation and maybe better correlation with the class labels you're looking for. Okay, so you can define some measure, right? So that will allow you to identify ones that are more likely to help. Okay, so you can view this as this kind of filter method. So it is more like a pre-step. Okay, so you take the data set, filter out like certain attributes, and once then you have the selected attributes, and that is what you kind of send it to the downstream process for the actual modeling. Okay. So that is simple, right? Quite effective, and it doesn't depend on what kind of modeling process you are going to use, okay? The challenge, of course, like whether you can come up with a good method to measure the goodness, right, of those features, okay? And then sometimes you feel, okay, yeah, maybe it's hard to kind of decide upfront, right, which features are good or not, okay? So then we have this kind of what we call wrapper method, okay? So at a high level, what it's trying to do is that I want to kind of do this together, right? The feature selection and the modeling process, they're kind of iterative. So it means I want to play with my feature set and also play with my model, okay? So that way you have this bit of kind of like this inner step, right? So you start with a whole data set with all the attributes, and then within this wrapper method, you're doing this kind of iterative process where you select some like feature subset, you construct a model, look at how the model is performing, going back, and then adjust the features you're using, okay? With that, right, when you're done, you would have both, right? You know which attributes you're using and also the model you have, okay? The last one, right? So as you can see, right, in this step, even though I have a wrapper method, but these two processes are still separate, right? Feature selection and the modeling, they're separate, okay? So another approach is actually to totally just combine. So this is called embedded methods. So within this combined step, you look at both the feature selection problem and the modeling for your classification problem. Okay, so you do that together, right? So you do this simultaneously, and when you're done, you have both. Okay, these are all have been shown to be quite effective. Okay, of course, again, comes back to your problem, comes back to like what you know already, right? And how big a data set, what kind of features you're playing with. Okay, but those are generally good approaches to consider. Okay, when you're trying to look at your data set and say, okay, I may actually be able to benefit from some feature selection instead of just sending everything in to the modeling process. Okay. All right, so that is a feature selection, okay? We're not getting into the details of the different methods, but if you're interested and that applies to your project, it may be helpful for you to take a closer look, okay? All right, next one, Bayesian belief networks, okay? This is actually related to what we talked about earlier for the naive Bayesian classification approach, right? Because earlier when we say naive assumption, that is because we assume those attributes are independent. Right? Because we're in the naive Bayesian classifier, we're calculating the combined probability, right, of multiple attribute values occurring together by converting that into the multiplication of the individual attribute probability. Okay? So the assumption is that they're independent. Okay, we say like age, income, or like gender, and then some like purchase behavior, whatever, right? We say that, okay, even though in the real world, right, some of them may not be absolutely independent, but they have been working generally well using the naive assumption, okay? But there are cases that the dependency is important to capture, okay? So if you don't utilize that dependency, your model wouldn't be very good. Okay, so this really gets to the point about, okay, we know that naive Bayesian classifier makes a strong assumption, right, about this independence, okay? But we know that many scenarios you do have this dependency. So if you want to be more specific, right, about those dependencies, that is what we're trying to do with this more explicit, okay, modeling, okay? So earlier, just say like everything's kind of equal, independent. You just do a simple multiplication. But now we say, okay, I have those different attributes. Okay, I want to actually put them into, in a way, it's more like a graph, right? But the graph is directed, meaning that you have dependency. So like you have the child depending on the parent node, right? So that you can construct a graph. Okay. So that you have those variables, right, representing different things. For example, we have the family history, being a smoker or not, non-cancer, positive X-ray. So all those things, right? You are leveraging some domain knowledge, okay? But you have those variables, right? You may not have the exact probability, but that's what we're trying to calculate, right? Because you have the data, you're trying to use that to observe and calculate the dependency, okay? So the high-level thing is that we're using this kind of causal model, okay? So it's a directed acyclic graph. Directed means that because one is depending on the other, right? Okay, and acyclic just basically says that you cannot have a loop, right? If A depends on B, B depends on C, and the C depends on A, then that is not going to work, right? If we have this kind of a circular dependency, okay? So once you have this graph, there are a few things, right? In every graph, you have your node, you have your link, and also we look at this parent-child relationship, because that's the dependency we're trying to capture, okay? Particularly, we're using this CPT, so this is what we're trying to capture, right? This is about the conditional probability. Remember earlier, say, naive assumption is that they're independent, right? So we don't care about the dependency. But in this case, we're explicitly modeling the conditional probability, okay? So what you're looking at is that, like, you have the table. For example, this is a lung cancer, right? If you look at it here, okay? So lung cancer or not, okay? So there are two cases, okay? And then you look at the parent nodes, because those are the dependencies you have, right? So you have parent node, family history, and a smoker, okay? Each of them can be positive or negative, right? They have it's the binary variable, okay? So that ultimately gives you these 4 possible combinations. Okay, so if you're trying to look at the lung cancer, right, probability of being yes or no, okay, you look at the family history, you look at the smoker, okay. So with that, then you can calculate the CPT, okay. So this is for the non-cancer one, okay. But the way we're looking at this, right, this is the general formula, right. If you look at each of that, like x sub I, so that's one variable, right, or one node in your graph. Okay, and then you're trying to look at the parents, right? So basically, you can say, okay, if parents is has those kind of values, then what is the likelihood you see the child with certain value? Okay. All right. So let's look at a more concrete example. Okay. So here, I think I have fire, smoke, alarm. Okay, so the idea is that, like, if there's a fire, what's the likelihood you will see a smoke detector goes off, or what's the likelihood of alarm going off? But also, if you have, like, somehow has tampered with your system, right? That also would change whether your alarm will go off or not, right? Okay, so that's my simple graph. Okay, so starting point is, again, I have this graph, right? We call it Bayesian belief networks, trying to capture the dependencies. Okay, all right. So in this case, I have, so ultimately we're looking at, right? So for any particular combination, right? Fire, smoke, alarm, and tampering, okay? So it is about the combined probability, okay? But you have the conditional probability, right? Because here, 5 fire and the tampering, so they don't have parent. So you have the probability of fire occurring, right? You have the probability of tampering, okay? And then you know that smoke has a parent of fire, okay? So now the probability is the probability of a smoke giving fire, okay? And then similarly for alarm has these two parent node, fire and the tampering. So that's basically saying probability of alarm goes off, giving fire and the T. Okay? All right, so that is what we're trying to calculate, right? You take the general representation, look at the specific graph, and then write it out like this, okay? Now you then, of course, you go to your individual node, look at the parent dependency, right? And then trying to calculate the CPTs, okay? So here, as I said, like CPT is showing the conditional probability for each possible combination of its parents, okay? So, so fire has a true or false, smoke has a true or false. Let me look at this one. So this is for alarm, I think. Yeah, this is for alarm, right? You have the two parent, fire and the tampering, okay? True, false combination, you have the 4 different cases, okay? And in the 4 cases, and then like whether alarm is true. So you're basically calculating the individual probability. So for example, like if you say false, there's no fire and no tampering, for your alarm to be going off is very small probability, okay? Or you can calculate another way, like if fire is true, there's a fire, no tampering, alarm is also very likelihood will be going off. Okay, so as you can see, right, those are just simple examples. But in the real world, you actually build pretty extensive, right, networks, because you may have quite a few variables you're dealing with. Okay, so in this case, with only 4, I can probably just manually calculate, right? But in a more automated process, you need a way to automatically, right, identify this. But this is not straightforward. How you train your Bayesian networks, right? When you have your Bayesian belief networks, okay, ultimately what you need is you need this graph structure, right? And you need the probabilities and the conditional probabilities and the combined probabilities, okay? All right, so to do that, right, you have, this is kind of iterative process because remember, it's directed, right? So you basically go from the parent to the child and then keep on going until you have calculated that for the whole graph, okay? But in the real world, you don't always have all the information, okay? So the simple case is easy, right? You have somehow figured a way you can actually write out all the variables. You can write out the graph, meaning that I have, say, like 100 variables, and I know how these variables depend on each other. Great, right? So in this case, all you need is just go through your data, right, and calculate the probabilities, because these are all observable information, okay? You know the structure, you know the graph structure, you know which variables, and those variables are all observable. So you know their individual cases, true or false or whatever particular value, right? So all you need is this statistical calculation of the individual probabilities, and then the conditional probabilities, and then the combined probabilities. Easy, well, or easier, right? But in the real world, you don't always have everything, okay? Now consider, right, the second scenario. I know the network structure, great, okay? But I don't know all the variables, because sometimes it's basically you have something that's hidden, right? So you don't, like, they're just information that you cannot observe, or they're like information that is not directly captured, right, in your network. So in this case, you have some variable, right, or some variables are hidden. So in a way, you're basically searching for those variables. You know there's some kind of hidden variables. So typically, we use this like gradient descent, right? This is like a general kind of search mechanism. But you're trying to kind of use a bit of kind of greedy algorithm to try to kind of converge, right, to the most likely scenarios, okay? So in this case, right, graph is known. Some variables are not known, so you need to kind of find, okay, the potential relationship, okay? In another case, I don't know my network structure, because sometimes you cannot spell out, right, exactly, okay, how they are related. You have those variables, right? So your variables are all observable, great, okay? But you don't know, right, how they're dependent on each other, Say I give you 100 variables, right? I have the specific values for all the different cases, okay? But I'm not giving you which one depends on which, meaning that you don't know the parent node who's pointing to whom, okay? So in this case, you're basically trying to figure out, right, which network structure, okay, is most likely, given what you have, what you can see based on the variables, okay? So in this case, you're basically searching through the model space to reconstruct the network topology, okay? Okay, so that can be computation expensive if you're talking about like large networks, because your number of nodes correspond to the variables you have, right? And then maybe a lot of kind of like, so the search space can be big if you don't have a lot of constraints, okay? All right, last one. This was almost like say, I don't know the network structure, right? And I have all hidden variables. That's almost like just like how to say a black blob. You don't have anything, right? You don't observe those variables. You don't know how they're connected. This usually in the real we don't have this, right? And we don't really have a good way of solving this, okay? But so far, right? Usually you see scenario 1, 2, 3 in the real world setting, okay? Best case when you have all of them, structure and the variables, but sometimes you're missing just one part of it, that's okay. You probably can still search or figure out the missing piece, right? But if none of that is known, then we don't have a good way, okay? All right, so Bayesian networks, right? High level idea, right? You're using those like graph structure to capture the dependency, okay? And it has been shown to be better, right? Of course, better than naive Bayesian classify, especially when you have strong dependencies in your variables. Okay, another one, okay? Support vector machines. Okay, so you may have heard this term in many different settings. Support vector machine, actually before deep learning, okay? SVM is probably like the most kind of like widely used and has been shown to be performing really well, okay, compared to many other methods, okay? Even nowadays with deep learning being advanced quite a bit, there's still many problem scenarios, like real world problem scenarios where SVM would have comparable or even slightly better performance, especially given the complexity, right, of SVM is still usually like smaller compared to like more extensive deep learning models. Okay, so what do we mean by support vector machines? Okay, high level thing, okay? So the term support vector are really just the data, right? Data points or samples, okay? So the idea is that you're trying to separate, right? This is the classification problem, okay? So somehow, if you have a simpler scenario, right? You have those like two different classes, right? You have the data points, and then you're basically trying to find a way to separate, okay? So you want to say, okay, you want to draw a line, and then you have a way of saying, if you go to this side, then that's one class. If you fall on the other side, that's another class, okay? So the support vectors are really those like objects that fall along those, what do we call margin, or this like, the idea is that you want to have some kind of clearance, right, spacing between the two classes. If they're like tightly like next to each other, it's very hard to, one, draw the line, and the second, even if you draw the line, the difference is so small, right? So your error margins are small. So what we're trying to do is that, okay, I want to draw a line, and I want to have like enough margin or maximize the margin to the two sides so that I have a good separation of the different classes, okay? So as we're illustrating here, right, in this like same data set, same two class objects, the first one, right, if I draw a line like this, yes, I can split them to these two, but my margin is small, right? Because the way I'm drawing it, you can see this is the margin I have to both sides before I hit a particular object on both sides, okay? Or if I can like shift the way I'm drawing the line, and I'll have a much bigger margin, okay? So the general idea is that I would like to have larger margin when you're trying to do the separation, right? Whatever line you're trying to find, okay, is like you want to maximize that, okay? And then we are using the support vectors to kind of define the space, right? Because this is just a line in a 2D space, but in a high dimensional space, think about this as a hyperplane, right? So the hyperplane are actually, of the two sides, are actually defined by those support vectors, because they really, can I say, this is the closest you will get to, right, from this side of the class, and then that's the closest you will get from the other side of the class. So they define the hyperplane, and that is how you are going to separate the classes. Okay, great, right? So this is in the linearly separable scenario. But you probably may have seen this, right? In the real world, it's not that clear. Okay, sometimes if you just draw it in, let's say, 2D space, you can see, yes, I can draw a line here, I can draw a line there, but many times you just don't have a way of drawing a linear, like line or hyperplane. Okay, so that means it's not linearly separable or linearly inseparable. Okay, so that's my example here, right? In this case, you really don't have a way of drawing a straight line. Okay. With support vector machine, okay, the idea is simple. Okay, as we have said, right? You were just trying to find those hyperplane, maximize the margin so that you can separate. Okay. So in my simple case, right? So this is what we do. Okay, you're basically trying to identify your hyperplane, identify those support vectors, so you have the margin. We just want to maximize it. Okay. So in the high dimensional space, right? You basically have this as a hyperplane. So it's like a weighted, like a linear composition of your vector, and with some kind of like a bias, then you actually have the hyperplane defined. Okay. So to find this, right, of course, you basically have to go to this high dimensional space, trying to figure out which ones are the support vectors to help you to kind of position, right, the hyperplane. Okay, so it takes some effort to train. Okay, especially when you have a lot of data points. Okay, if you have a high dimensional space, a lot of data points, it does take time to train. But once you have trained it, once you have found this hyperplane, right, using it is fast. Right? All you need to do is just doing this calculation, right? And see which side of the hyperplane you're on, okay? So it takes more time to train, but the online classification is pretty fast, okay? All right, great, right? But this is for the linear case. As I said, if it's a linear case, if you can have this, find this hyperplane, you're done, okay? But what happens, right? It's not linearly separable. Okay, so this is the first case, right? So if it's a linear inseparable, okay? So if it's like, say, roughly there, but like not exact, sometimes you can play a small trick. That's just making a little bit of approximation. So that means I may not have a clear separation, okay? But I'm okay if you're making some small mistakes, okay? So this is what we're like trying to use what we call is a soft margin support vector machine. Okay, so I will still draw this linear hyperplane. Okay, knowing that like I may have something that is kind of like maybe falling a little bit closer to the other side. Okay, and that is what I'm trying to capture. So I'm using what we call a slack variable. Okay, so like how much slack I'm cutting you, right? So that you can still have your linear separation. Okay, so generally, like the idea is that okay, if I'm okay if you're making some mistakes, right? So I may have a smaller kind of like control value, meaning all cost in a way, right? If you're making slight mistake, like that's fine, then it's okay. Versus no, I prefer you really don't make mistakes. So you can actually adjust that control variable, right? So that you're putting like more weight on, yes, I don't want to make a mistake, versus, yeah, I'm okay making a mistake, but I want to have actually good separation, okay? So that's really the trade-off, right, between the penalty and the margin, right? How big a margin you can have, but also given that you could make mistakes, okay? So you can see, right, with the linear separable case, then that could be a special case. That means I can give you a slack of 0, and you would still have a max margin, right? Okay? But this only works to some extent. As I said, right, if they're close, so I can have, like, meaning that I can still separate them, not like a big margin, but still reasonably good, fine, right? That works. But there are many real-world cases where just so mixed. The different classes are so mixed, I don't really have a way. Even if I'm cutting like some slack, I may still not be able to do it. Okay, so here is an illustration, right, of how the slack variable, right, can impact your results. Okay, so what we're showing is that like I have like different penalty strengths. Okay, this one has a 0.001 versus 0.05. Sorry, I cannot read it. 0.05, this is the 1, and then this is the 10, right? So you can see, right, I'm increasing the cost, meaning that like here, I'm giving you more slack. That means, okay, you can make a mistake, the penalty is not that big, right? So you can naturally see right now I'm actually within my margin. Remember, this is the hyperplane and I have the margin. I have quite a few points that are kind of falling within the margin, which is not what we want, right? But in this case, since they'll say, yeah, it's okay, you make some mistakes, right? So I'm actually allowing more mistakes, okay? But as you increase, right, the penalty, okay? So if the penalty, let's say when it gets 10, that means I really don't want you to make too many mistakes, right? So each mistake carries a higher penalty, right? So in this case, you would like have as you can see, like now your margin is much smaller because you don't want to make mistakes, right? So as we increase the penalty strength, okay, we have smaller and smaller margin, okay? And then the points, of course, like that will be misclassified will also reduce because now you have much tighter margin, okay? So that's the general idea, okay? But there's only certain like amount you can do. As I said, like if the data is just mixed everywhere, then it's really like not easy for you to find something that would work just using this linear hyperplane, okay? So this goes to the other approach, right? They don't say, okay, yeah, I cannot really do it, right? The linear hyperplane, even with some kind of fuzziness, still doesn't work. So the other idea is that if the current space, right, is too small, meaning that in the current space, things are really mixed up, okay? I want to project it into a bigger space. So remember, when you add new dimensions, right, you have much bigger, it's exponential increase of the space. Okay, so if you're taking a data set which is mixed in the lower dimensions, project into the bigger space, they become more sparse, right, in the high dimension space, and then you're more likely to find a hyperplane that can separate them. Okay, so that's a high-level idea with this approach. Okay, so we want to transform the data, okay, from the lower space to the high dimension space, such that we have a bigger space, a sparse, more sparse space to work with, okay? But then, of course, the thing is like if you're transforming everything from the lower dimension space to the high dimension space, the computationally, right, it'd be actually much more expensive. But turns out, right, we actually have a good mechanism, okay? So mathematically, we can actually find those kernel functions, okay? Meaning that if you apply the kernel function, okay, it is mathematically equivalent to projecting, like doing the dot product in the high dimensional space, okay? So if you have, like, say, x sub I, x sub j, so these are two different vectors, right? So you do the kernel, apply the kernel function to them, and then that is equivalent to the high dimensional space relationship, okay? So once we have that, right, as you can see in the simple example, right, earlier in this two-dimensional space, I really don't have a linear way of separating, right, them. But once I project them to this, I think it's only 3D, right? But 3D now actually have a way of kind of separating the blue points from the red points. Okay, so two key ideas. One, projecting to high dimensional space so that I can find a linear hyperplane, right, to separate the classes. Second, I actually don't need to do this in the high dimensional space. I can use a kernel function to do this in a more efficiently in the original lower dimensional space. Okay, so there are, of course, a lot more, like actually different types of kernel functions. Okay, so here I'm listing a few. Those are typically used, and they are, of course, the different library implementation to support this. Okay, so you can play with this, right, to see like how those may apply to a particular problem setting. Okay, there are a few implementations as well. So libSVM, SVM Lite, I think more recently SVM Torch. Those are actually implementations. So you can just try this out, right, with your data set, right? So you don't necessarily have to implement everything. But this has shown to be very powerful, okay? And has been shown to be very effective, right, in many real-world data, okay? So the high-level thing, right, this is actually just say, if you think about SVM, you're drawing this line, right? Like in the linear space, it's a one line, one hyperplane. Okay, in the high dimensional space, it's still a hyperplane, but like it can actually capture those kind of bit of more curved relationship, right? But that's only one side, because if you have hyperplanes, this side or that side, so it's naturally like a two-class classification mechanism, not like a decision tree, not like a Bayesian classifier, right? Because those actually can naturally work with multiple class labels, okay? Here, it's one or the other, okay? So it's a binary classifier, okay? So now then you ask this question about how do you handle multi-class classification, right? So in the real world, it's not always a binary classification, okay? So naturally, you can have these two, okay? One is called one versus the rest. So meaning that, okay, let's pick, right? Red, blue, green, okay? So you can say either it's a red or not red, right? That's a simple, like a binary classification. And then it's a blue or not blue, okay? Green or not green, okay? So that's how you can convert your multi-class classification problem into this multiple binary classification problem. And then you can use a support vector machine, right? Okay? Or you can do this one or the other, one versus one, right? So it's like red or green, red or green, red or blue, blue or green. Okay, so every time you're doing a pairwise comparison, right? So you can already calculate, right? Depending on how many classes you have, right? If it's n classes, then you have n classifiers, because you basically have one for each, right? One is like, are you this class or not, this class or not? Okay, so that's n total classifiers, okay? While if you're doing the pairwise, then you basically have to do n multiplying a minus 1 divided by 2, right? Because that's the pairwise, the possible pairwise combinations you have, okay? All right, so this is just one thing to note, right? Support vector machine, it has binary classification, and you need this mechanism to allow you to work with multi-class classifications. Okay, to summarize, right, support vector machines are widely used, okay? The key thing is that it can work for both linear and nonlinear data. Some of the key concepts, right? What is a support vector? What is a margin? Do you want a smaller margin or bigger margin, right? So that's the high-level thing we're trying to capture, right? So using those support vectors to help you, right, to divide, right, or separate the different classes, and the bigger margin is what we're looking for, because bigger margin gives you more separation between the different classes. Okay, but there is a little bit more when you talk about SVM. Okay, so SVM, as I said, has been shown to be working really well, right? But it does suffer a little bit from the scalability angle, because if you think about it, right, you have all those data points, right? Usually you need to project it into a high dimension space and then look for this hyperplane. So it does take some time, okay? Because you need to find, right, the support vector, the hyperplanes, okay? So typically, SVM, we will say that it takes time to train, okay, pretty fast in the actual classification. And it works well for high dimensional data. This is important, right? Because a lot of times high dimensional data are very difficult to separate, okay? Many of the existing methods, right, if they're like a linearly non-separable in the low dimensional space, right, they don't have a good performance. The performance actually can be pretty bad, right? But SVM, because they can work in the high dimensional space, okay, it turns out it actually can work with, if you have high dimensional data and you have a classification problem, SVM usually works well. So performance accuracy is pretty good, okay, when you're using SVM to classify high dimensional data. But just know that it may take some time for you to train that, because that does depend on, like, you basically need to go through all the different data points, and you need to find this high dimensional hyperplane. Okay, so there's just the paper has a reference, but you can also look for this paper by the title. This is actually very interesting work. So this is from KDD 2003, a while back, right? But the notion is very interesting, because what it's doing is just like, oh, I know SVM, like if they need to look for all those individual data points, it doesn't scale well, it's too slow. But naturally, in the real world, right, those data points are not kind of say uniformly spread in the space, right? So you want to do some kind of clustering. Okay, we'll be talking about clustering later. But the general idea is that if you have clusters, you can actually combine them, right? So this is what I call as a micro-clustering approach, so that I don't need to look at the individual data points, rather treat those microcluster as a supernode to some extent, okay? That can help you to reduce the number of vertices, like nodes you need to work with, and actually can make the process more efficient, okay? All right, okay, next one, rule-based and pattern-based classification, okay? So we have been talking about, right, earlier, it's like the decision tree, but it turns out you can actually write out just the rules, okay? So decision tree asks us at each level, right, one question, like, are you a student or not, right? What's your credit rating, right? And then make a decision, okay? But here, you can literally just take that and combine that, right? The multiple questions you're asking and the branching conditions, that can actually turn into a rule, what we call if-then, right? So if certain conditions are met, then I can make a decision about the class label, okay? So this one is very easy to use, right? If I give you this rule, like you can just take the rule and follow it, right? And then be able to use this rule to make your classification decision. Okay, so the format is simple, right? You basically have this if part and the then part, okay? But there's actually some important thing, because ideally, right, one rule be, say, sufficient, right? You use one rule, and then you can already classify yes or no with all the cases. But each rule only covers certain scenarios, right? Because your rule is asking about certain conditions, okay? So if I'm just giving you any particular sample, right, it may or may not satisfy the conditions of your rule, okay? So this gets to the point of this coverage, okay? So coverage means that out of my whole data set, okay, how many of those data points would satisfy the conditions so that the rule can be applied? Because if the conditions do not satisfy, then I cannot use this rule, right? For example, you say if my rule is about, is age and then whether a student or not, right? That of course covers a subset of my population, but there are many others that may not even satisfy this rule, so they cannot be classified using this rule, okay? So that is a coverage piece, okay? The other one is about accuracy, right? So that means among the ones that actually are covered by my rule, and then now I can make a decision, right? But is that decision correct or not, okay? So that's the accuracy piece, okay? So do you want a higher coverage or lower coverage? If you're choosing a rule, everything else being equal, do you want a high coverage or low coverage? High, right? High is better. High means that this rule can cover many of my cases, right? Okay, so that's good. And then naturally, you probably want a high accuracy, okay? But sometimes you have to make a trade-off between these two. Okay, so let's look at my example here. Same table. So I'm using this rule, right? So if the age is at most 30, and this is student, and then I say, okay, this person is going to purchase a computer. That's my rule, right? So first I'll just check the coverage. So I need to go to my table. Okay, so here I quickly identified out of my 14 cases, 2 of them actually satisfy the conditions, right? It's about the age and the student, right? Okay, so these are the 2. So what is my coverage? I have 14 total, 2 cases match my conditions. Which one divided by which? 2 over 14, right? Because the size of the data set is 14 and the coverage is 2, so that's my 2 over 14 case, okay? What about accuracy? So in both cases, right, they match my condition, and my decision will say they are going to purchase a computer. Did they purchase a computer? Yes, yes. So what's my accuracy? Out of the 2 cases, 2 matches, 2 by 2, right? So I'm correct all the time, okay? So in this case, I have coverage 2 out of 14, and I have my accuracy, which is 2 over 2, okay? Now, look at this case, all right? I have 2 rules, okay? This is rule 1, this is rule 2, okay? So I have rule 2, as you can see, right? So within that rule 2, we covered 2 cases, okay? And within that is actually perfect accuracy. Both are correct, right? Well, with my rule 1, I have much bigger coverage. I'm covering quite a few, but I have a couple of mistakes or ones that are different, okay? If you need to choose, which one? R1 or R2? If you get to pick one. One, right? Because in this case, even the R1 is not a perfect, right? It actually covers many of my cases, all right? Okay, but of course in the real world, right, you usually don't have to pick just one, okay? You want to use a like combination of multiple rules so that hopefully you can cover, right, all the cases with good like accuracy, okay? But many times unless for the corner cases, because you don't want to be picking like smaller rules, each one covering like 1 or 2 cases to have perfect accuracy, right? Then you have too many rules, your model is too complicated, okay? So ultimately it's about some kind of trade-off. Yes? Yeah, the question is that like usually like do you have some kind of threshold to say you have to above a certain accuracy for it to be useful, right? Typically, yeah, accuracy you have like you need to meet certain bar, right? You need to say because I don't want to be working with a rule that's not good enough. Okay, so there's usually a notion of the accuracy means that it needs to be accurate enough, and then I go for bigger coverage. Make sense, right? But still, there's no hard threshold, okay? Depends your problem. Like many times people say going, let's say above 90%, but sometimes you say I have to be even higher for that to be useful because it gets to the point about false positives, false negatives, right? Sometimes say, okay, I really need to be more accurate versus, yeah, I have some kind of like flexibility in terms of how accurate this is. So typically you pick high enough accuracy and then go for higher coverage, okay? All right. Now this is another related problem. Okay. So this is when you have like multiple rules being triggered. Okay, triggered meaning that they all satisfy the conditions, right? Because earlier we say, okay, what happens if like none of the rules apply? Fine, right? I don't have a way to do my classification, but this is the other side of the problem. Okay, given a particular instance, okay, somehow I got multiple rules. Okay. Multiple rules now satisfy this particular like sample. And they say things differently. Okay? Now this gets to the point about which one do I go with, right? Because like say one rule says it's only checking about the age, like at the age of the customer. The other rule is asking about the credit rating and being a student or not, right? But they all satisfy this particular instance. Okay, so best case, if the only rule triggered, great. No rule triggered, you need to figure out something, right? But you have more than rules triggered. How would you choose? Earlier we talked about accuracy, coverage, right? So coverage is one, but right now they're all triggered, meaning that they all apply. So you want to probably go with a higher accuracy, right? Or if there are multiple ones that have comparable accuracy, but they have different decisions, you may do some kind of majority vote, right? So like 2 rules says that it's a yes. Another rule says no, right? You can go with a majority vote. You can do some kind of weighted majority vote if you look at the accuracy. There are different ways to do it, okay? And sometimes just really domain knowledge, okay? We don't make it easy, right? So size ordering, that's basically say, okay, which rule is checking more information? So that means it's more detailed, right? More informative to some extent, right? If that rule is asking for more information, okay? And also you look at, the importance, like false positive, false negative, majority, right? So then you actually also have a way of saying, okay, I know multiple rules have triggered, but I want to pick this class label because this class label has like certain property I'm going after. And then a lot of times, really just say if you have some, domain knowledge, okay? So that you may have a way of saying, okay, I want to prioritize, right, those rules over the other rules, okay? So no, let's say, definitely less, but just knowing that you have those situations, you need to do your reasoning, right? Each rule, you look at the accuracy, you look at the coverage, and the combination of those rules, because ultimately you're going for the total, right, performance when you are applying your set of rules, okay? Now, how do you generate your rules? Okay, since we mentioned decision tree, we already have a pretty direct way of getting the decision, getting the rules, okay? Because what we do with the decision tree is that it starts with from the top, right? Ask one question here, follow one branch, ask another question, follow another branch, get to the leaf node when you make a decision, right? Okay, so basically you can just take those, right? So each branch or each path from your root node to a leaf node, that is a rule, right? Because it's asking certain conditions and then getting to the leaf node so that you can make a decision, okay? Now, in this case, I'll just first write out, right? What do you have, right? Those are the different rules you can get. But what's important to note here is the rules are exhaustive and mutually exclusive. What does it mean? Exhaustive, meaning that I'm actually generating, right, all the possible ones. So you're checking all the possible combinations, right? So this is the same with the decision tree. Every time you do branching, your whatever condition you have, right, you must be following one branch. You wouldn't have a, like say there's no way for you to follow a branch before you get to a leaf node, okay? So it must cover other cases, all right? But then the mutually exclusive, what does it mean? Meaning that the rules are different, right? The conditions are different. Because for you to be branching differently, that means you must have something that's different along the way, right? So you wouldn't have two rules satisfying the same thing. Make sense? Okay, so this is good, right? This is what we want, right? We want a rule set that is exhaustive. That means it covers different cases, and those rules work differently. They're not overlapping. Okay? All right. Now, there are, of course, different ways, right? Decision tree is a good way. You construct a decision tree, convert it into the if-then rule, you can apply it, right? That kind of sounds a little bit extra, right? There are other approaches, okay? So without actually constructing the decision tree, I could just look at my sample, right? This is what we call you learn directly from your training data. You don't construct a tree, okay? So every time what you do is that you, at the very beginning, you don't pick anything, right? And then your decision is just whatever you prefer, right? Either the higher percentage of that class label, or say I always want to accept the loan, right? So that you have your default decision, okay? But then as you go down, right, you can use this greedy depth-first strategy. So that means I'm trying to add, right, some conditions to my rule, okay, by looking at my data set. Okay, so my starting point is this, and then say I'm trying to ask, say, no term, like short, long, whatever. So you're basically choosing one attribute, right, with some value, okay, and then see what you get, okay. And along this, right, it's depth first because it's a greedy approach, right. So you pick one, you make it more specific, and if the accuracy is still good, coverage is still good, you keep going. Right? So that is the idea that, okay, I'm not constructing a decision tree, but I'm just using my training data to guide me. It's more like a rule of thumb to some extent, right? Like what is more like the majority case, right? Which information in combination give you a good, a majority related to the class labels, okay? All right, another one, okay? So rule basis, you use the if-then rules, right? But there's another rule we actually learned before, which is the association rule, okay? Remember earlier when we talked about frequent patterns, we talk about associations, that actually already give us very good information, right? If something happened, there's a likelihood of something happening, right? So we're just working on this problem, say you have the support value, you have the confidence value, right? This actually is something you can apply to classification. Because if you look at the attributes, right, if you have those properties happening, right, and then using your association rule, say, okay, then this is likely to happen, right? So this actually translates, right, directly, right, into our classification problem, okay? And this is particularly useful because earlier, right, with the decision tree, with the Bayesian classification, they're working with attributes, right? They're working with specific attributes, attribute values. But when we're learning patterns, we're actually trying all the possible combinations, right? So our frequent pattern mining process already give us some good combinations of information, okay? So my example here, right? So if you're using like a standard approach, you may be looking at the individual word in the document. But here, if you say like apple pie or apple iPad, if they're occurring frequently in your data set, you naturally have that as a combination, right? So you are already taking those words together because they occur frequently. And that is a condition you can use for you to apply that. So that's why I say we're allowing the pattern mining and the classification together, right? So we're using the pattern-based classification. It's utilizing the patterns we have learned to come up with the classification decisions, okay? All right, so this actually has shown to be quite useful, especially like if you're in your project, if you're trying some frequent pattern mining, right? And then see whether the patterns you have found can already be useful for your classification problem, okay? All right, one more, weakly supervised learning, okay? We said classification is a supervised learning, right? We're using training data, the predefined class labels to train the classifiers. We also talk about ensemble so that you can have multiple classifiers, combine them together. So what do we mean this weakly supervised learning? Okay, so there are a few things that's actually quite relevant. Okay, you may have heard these terms under different scenarios. Okay, so these are all related. Okay, they actually tackle different perspectives, but combined, right? They can be very useful for your classification problem. Okay, first one, semi-supervised learning. Okay, we'll talk about supervised learning and unsupervised, right? So somewhere in between is this semi-supervised learning, and it's actually getting a lot of popularity, a lot of research is going on here. Okay, the high-level idea is simple. Okay, so somewhere in between, right? Supervised learning means that I have labeled data. Unsupervised learning means that I don't have, right, labeled data. Okay, so I can say if I only use the label data, it's too limited, right? So my model may not be that good. I do want to use the other information. But if you only use the unlabeled data, right, without the labels, you're really kind of like leaving out some valuable information, okay? So what we want to do is that we want to use both, okay? So how do we do it? There are two approaches, okay? First one is called self-training. That's simple, okay? It's an iterative process, right? So I take the labeled data, train my model. That's my classic, right, supervised learning step, okay? Once I have trained my model, I can apply my model, right, to the unlabeled data. And I can make a classification decision, right? So especially for the ones that I have high confidence on, I can pull them in. Right, so you say, okay, using my model, like I can classify certain portion of those unlabeled data. So I pull them in as labeled data. Now I can even update my model, okay? So that's what we call self-training. You're training one classifier, okay? But you're improving, right, with more and more labeled data points. The other one is called co-training, okay? Co-training actually has been shown to be more effective. Because self-training, you may be kind of inferencing, right? You're basically kind of like reinforcing potentially mistakes that you have made, right? So you're basically just learning among yourselves. But the co-training is actually interesting. The idea is that they are using different views, okay? So you're training two different classifiers. They're using different information, okay? And then you're trying to classify each other. Okay, so as a name, like so the illustration here, right? So is very beginning. I have a few positive examples, negative examples, and I have quite a few that are not labeled. Okay, so this one, say I can take one classifier. I'm training on view one, so that means I'm using partial like view of the data set. Another classifier, same thing, another view. Okay, so that means they're being trained on different types of information, even though it's the same data set. Okay, and once they have it, the best way, okay? Once I have it, right? So then I can use this like basically like then I can allow each of them to label some of the instances, and then they can like kind of continue, evolve. But because I have two different views and two different perspectives, right? The model is actually more stable, and they have been shown to be more effective in this kind of semi-supervised learning scenarios. Okay, another one, active learning. Okay, I know we're using a lot of terms, learning, but they are different, right? So active learning has a slightly different problem. Here the case is that, yeah, I don't have all the 10 cents labeled, okay? But I have access to somebody or some kind of oracle who can then help me to label something. So you can view this as either say, I know like it's like human labeling is expensive, right? So I cannot ask this human expert to label everything. So I want to be selective, right? So I want to be selective in terms of which questions I present, right, to the oracle, to the human expert, okay? So because many times if you look at your data, right, your problem, right, some of those are easy or easier, right? So you can probably say, okay, yeah, I'm fairly confident about those cases, okay? But when you're not as confident, right, or say, I haven't seen this before, right, I don't have enough information to classify this one, then you go to your supervisor, right, go to the expert, right, and then you can ask for like a more dedicated, right, label, okay? So the question here is all about which ones to label, right? Because you want to be able to figure out, right? So there are different approaches, right? Uncertainty, sampling, vision space. So basically just say, okay, how much you know already, how confident you are, right? For you to then pick the ones that you want to get the labels for, okay? Another one, transfer learning. Transfer learning is actually very popular these days, right? And it has been shown to be useful in many cases, okay? The high-level idea of transfer learning is actually simple, okay? So in a general learning case, right, you say every time you have your data, you have your sample, you have your training data, you train your model, you're done, right? And then when you have a new problem, you do the same thing, right? Get the data, train your model, and build a model specific for your problem setting, okay? But sometimes you found that, hey, there's some relationship, right? So whatever you have spent your effort on training one model in one setting may be leveraged in another setting instead of doing something from scratch. Especially like for the second one, you may not have enough like information or labeled data to work with, okay? So a lot of times that, okay, you have more like a heavy effort, right, like base model, and now you want to be able to just adapt for the new problem setting, okay? So my simple example here is about like sentiment classification. It's like you're looking at the customer reviews and you're trying to figure out whether customer like this product or not, okay? So assume you already did this, right, for like say cameras, okay? And now you want to do this for TVs, right? Or you say did this for cars and look at for trucks, right? As you can see, right, those are different, right? Different problems, but there's some underlying relationship or knowledge that you may be able to leverage. Okay, so the high-level idea is that instead of doing this like individual, right, system for the individual things, I'm trying to use my source task. That means something I already learned, okay, and then transfer to the new task that I'm trying to target. Okay, the question, of course, what you can transfer, right? Because you know attributes may be different. The class labels may or may not be exactly the same. So there are actually a lot of research on this topic, and actually has been shown to be very useful in many of those real-world scenarios. Okay, so transfer learning is another right very powerful mechanism, and definitely check it out if it applies to your project. Okay, distance supervision. Okay. This one has a slightly different angle, okay? So all the previous ones are just we're trying to learn, build a better model, the modeling process can be improved further. Here we say, okay, but if the underlying problem is about you just don't have enough data, right? Like even you don't have enough data, you cannot train a good model, okay? So the distance supervision idea is really just say, I want to create more data points. Okay, in a way, synthesizing, right? Or generating data points that would allow you to build better models, okay? So here, the idea is that I want to generate a lot of data points, right? That's important, right? If I'm just generating a few, that's not really going to help. I need a lot of data points. But of course, it's not easy, right? So I say, okay, so I'm going to generate a lot of data points, but they are potentially like not as good, right? So they'll be noisy in many ways, okay? But ultimately, you want this still be helpful, right, for your modeling process, okay? So for example, like say here we have like Twitter sentiment classification. Okay, so how do you take a tweet like message and then say, okay, is this positive or negative, right? So you can create some simple rules like if I see a smiley face, I think it's a positive. This person is happy about what they are saying. If it's a sad face, it's different, right? So you're using some kind of heuristics, okay, to help you to generate, right, a lot of data points. Hopefully, would then help augment your classification problem. Okay, so there are different ones. Okay, but of course, like you say, this is like sound easy, but it's really hard for your real world problem, right? Sometimes you may be able to have some reasonable heuristics to generate good data. Sometimes just not easy. So a lot of times you're talking about like how applicable, right? Again, accuracy coverage, right? If you're using a particular rule, how do you know whether the rule you're applying to generate your data points are good or not? We have a couple more knowledge I would quickly mention. Zero-shot learning. Okay, this one is also actually very active research topic these days. Okay, the idea is simple, meaning that you want to learn something that you haven't seen before. Hard, right? How do you, like say, if I have trained a classifier, okay, say now I want you to do a like animal classification, right, of animal ABC, okay? And now I'm giving you a complete new thing. You've never seen it. Can you classify what it is? Then the question is, oh, I have never seen it. How do I even do it, right? This actually relates to the transfer learning thing, right? Because you have some underlying knowledge, okay? So for example, if you look at animals, right, they have certain attributes or features, right, that help us to differentiate things, okay? So that's what we're trying to do, right? We want to leverage external knowledge or some kind of side information, okay, even though we've never seen this before, okay? So look at there's just one specific example right here. I think they have like a dog. Okay, not really tell what they are. So they have some like semantic attributes, right? Whether they have 4 legs, whether they have wings, whether they have retractable claws, whether they have super night vision. So those are things we have somehow learned, right? You have some kind of semantic attributes that you have learned by looking at other previous data, your training data, right? Now you're being asked to do something that I have never seen. This is a new animal nobody has seen before. But you can apply some of the similar kind of semantics, right? The attributes we have, look at it, okay? So with that information, then you may be able to, even though you say I cannot classify as whatever I have seen before, but I can roughly classify, right? Which maybe bigger category it is belonging to, okay? So that's a high-level idea. Again, there's like each of those actually has a lot of details, a lot of techniques, a lot of active research going on. So we don't have the bandwidth to cover everything, and we're really just kind of pointing you, right? There's a different like directions that people are working on. But those are interesting and very important problems, okay? All right, 2 more minutes. So I want to talk about different data types. Okay, so earlier we say those are so far, right? You're talking about like different attributes, right? Those are usually categorical value, numerical value, and then you're trying to like do some classification based on like the particular values or the calculated distance. Okay, but there are different ones. Okay, stream data. Think about we have been using the fraud, right, detection, right? So you have some kind of like transactions. You have a lot of transactions. You're trying to determine which ones are fraud or not, okay? So we had this for the false positive, false negative discussion. But many times you don't have one data set that is static, right? And then you just say within the static data set, you build a like classifier to say this is a fraud that is not, okay? Instead, you have this continuous stream coming in, okay? Think about like transactions happening all the time, right? So if you're in like sitting in the fraud like detection department, you basically just need to monitor that, okay? So it's a stream data, okay? I need to classify it, right, quickly, okay? So if you want to use this kind of traditional kind of like iterative process, say I want to take a training set, build my model, right, test it, it's good, I'm using it, and after a while I get a new data set and then retrain my model or update my model, and then I like deploy the new model. That used to work, okay, when I think earlier days, I think people are talking about like fraud detection within like weeks, right, like weekly report kind of thing. But nowadays, it's really happening kind of in a split second, right? As it's happening, you want to decide, right, whether this is a fraud or not, okay? So this is a general challenge related to stream data, okay? High arrival speed, infinite length, one pass constraint, and also concept drifting, okay? Meaning that data is continue coming in. You don't really have the time to go back and like redo everything or recheck something, right? You just keep going, okay? And also, things may change. So your model, right, would be changing. You don't have one model and it's set, okay? Because the fraud like transaction, they may always try to come up with new mechanisms or new strategies, right, to overcome or go undetected. So a lot of that, we use this as an ensemble approach. Okay, we talk about ensemble, right? So what we're doing is like we take those streams, we build those as chunks, right? Each chunk, well, I now build like a classifier, and then I'm basically just ensemble those chunks based models, right? And I weigh them differently, because typically I'll say I weigh the recent ones more like higher. So that means they're more important, okay? So over time, I have some knowledge from the history. I have better knowledge from the current, okay? And over time, if the model is changing or the like fraudulent pattern is changing, I can still adapt my model, okay? So that's the high-level idea. We're going to stop here. We're out of time, okay? Reminder, please finish the survey for the midterm exam by Thursday, and homework 4 is due by Thursday. Thank you.